Lab 1 presentation by Daniel Manuel. Introduction. The purpose of this lab is to observe the motion of an object at constant speed without changing direction. The object's motion will be captured using Tracker and then simulated in GlowScript. The physical principles that are being observed are Newton's second law or the momentum principle. Briefly, about the conclusion, the simulation of the object's movement has a greater position value than the value outputted from the tracker. The reasoning will be explained later. The object being studied is a ball rolling at constant velocity, and here is a video of the motion of that object. The system is a ball rolling, and the surrounding is the floor that is rolling on. Relevant principles. Newton's second law. The ratio of the change in velocity to the change in time is equal to the net force acting on the object divided by its mass. And there is the equation for that. This principle is important to determine that the net force of the object in motion is zero, since the velocity is constant in the motion study. This also means that initially the velocity should be equal throughout the motion, and within Tracker, the initial position of the object is centered at the origin of the graph overlaid on the video. Here is the formula for the predicted final velocity and the velocity. Experiment details. For Tracker, within this Tracker software, the range within the object's motion could be classified as constant, and it is trimmed down to the usable constant velocity. An axis is centered over the object in the first frame so that the displacement can be measured. The video is also calibrated using an object of known length within the video, which is the level in the lower right-hand corner. Within each frame of the object's motion being studied, a point mass is placed in the center of the ball until the final frame. With the displacement and time information extracted from the video, a graph can be created to compare it with the Python simulation. Coding details. The code is copied and pasted into GlowScript. The information that is needed to be included/changed into the code includes the ball's mass, position, and velocity. The time of motion, change in time, and the update of velocity and position using the momentum principle are also needed. The initial velocity vector is 0.00156, 0, and 0 meters. This is obtained from the tracker position at time equals 0 seconds. The ball's velocity is obtained by using the following formula. The first two recorded data points in the tracker are used for this calculation, and since the motion is in the positive x direction, the velocity calculated will be in the first position. This is the vector for the ball velocity, 2.1700 meters per second. The updated ball velocity and position variables are directly from Newton's second law rewritten. You can see this on line 59 and 61, where it says ball.vol is equal to ball.vel plus fnet divided by ball.m times delta t, and on line 61 as well. The time is the terminating condition of the while loop, and it is taken from the end of the object's motion. T is less than 0.734 seconds. The time of each time step is the delta t variable of 0.033 seconds. GlowScript versus Tracker. To the very left of the screen, you can see the Tracker position versus time graph and the Python GlowScript position versus time graph. In the middle are the tables with those data, and the values for position of the GlowScript at the same respective times as the Tracker are slightly increased. This could be due to the force of friction not being accounted for in the GlowScript simulation, or due to the small variations in placing each of the mass points in each frame of the Tracker. Variations in each positions that are estimated to be the center would cause a different value than the simulation. Another difference is the timing between the two. The time does not start at 0 for the GlowScript simulation. What if? When you analyzed your video data in Tracker, you made a choice of the orientation of the axis. If the orientation was changed, and instead of the object moving in the positive x direction, it moved in the negative x direction, then the magnitude of the velocity will not change, but the direction of the velocity would be in the negative direction instead of the positive. All the position measurements would be negative instead of positive as well. What does it mean? Is it possible for you to say how many pushes and pulls, i.e. how many forces, are added together to give zero net force in the case that you observed? So if we were to draw a diagram of the forces acting upon the ball, we would see gravitational force acting in the negative y direction, the normal force acting in the positive y direction, force of friction acting in the negative x direction, and the force applied to the push of the ball in the positive x direction. Assuming that we are looking only at the motion of the constant velocity and the force that was applied to the ball was parallel to the floor, then we can see how the combination of forces gave us the net force observed, which would be a movement, a constant velocity in the positive x direction. Conclusion. The glow script model did well to predict the motion of the ball, as it did in real life. However, it could be improved. Some improvements may include an addition to the force of friction, so that outputted results do not show the increased position values in the simulation than compared to real life.